Hello everyone, myself Bhuvaneshri VS. I am currently pursuing my civil engineering in SVC Bengaluru. Today we will be discussing about design of footing. Introduction to design of footing. Footings are structural elements that transfer load from a structure to underlying soil. Proper design of footing is essential to ensure stability and safety of a structure. Factors such as soil type, building loads, and environmental conditions must be considered in footing design. Types of footings. Common types of footings include spread footing, mat foundations, and pile foundations. Spread footings are used for individual columns, while mat foundations are used for entire building footings. Pile foundations are deep foundations that transfer load through friction or end bearing. Design considerations for footings. Footing size and shape are determined based on the structural requirements and soil conditions. The depth of footing should be adequate to prevent settlement and ensure stability. Footing reinforcement such as rebar is essential to resist bending and shear forces. Let's look into an example. Design a rectangular footing of uniform thickness for an RC rectangular column of size 450 mm into 600 mm bearing a vertical load of 1000 kN. The safe bearing capacity of the soil may be taken as 1 kN per meter square and use M20 grade concrete and Fe415 steel and sketch the reinforcement details. In step 1, we will be writing the given data, that is FCK, characteristic strength of concrete, that is 20 Newton per mm square. Fy is characteristic strength of steel, that is 450 Newton per mm square. Column size, as it is mentioned in question, it is 450 mm into 600 mm. By looking into the dimension, we will be knowing that this is a rectangular footing. And safe bearing capacity of soil is 180 kN per mm square. In step 2, we will be determining the area of footing, that is total load is equals to column load plus self weight of footing. In question itself they have mentioned the column load, which is 1000 kN, and self weight of footing is always taken as 10% of column load, that is 0.1 into 1000, which is 100 kN. Therefore total load is equals to column load plus self weight of the footing, which is 1100 kN. Further, we know that safe bearing capacity of soil is equals to total load by area. Safe bearing capacity of soil is 180 kN per meter square and total load is 1100 kN. We have to determine the area. But by cross multiplying, we will be getting area as 6.11 meter square. Then, since it is a rectangular section, area will be equals to length into breadth, which is equals to 6.11 meter square. Then we have to determine the overall length and overall breadth of the footing. So we should provide equal ratio for column and footing. Since we are knowing the length and breadth of column, we should provide the equal proportion, equal ratio to determine the length and breadth of the footing. That is L by B is equals to 0.6 by 0.45. Then L by B is equals to 1.33. Then length is equals to 1.33 times B. We know that length into breadth is equals to 6.11. By substituting value of L as 1.33 B in this equation, we will be getting the value of B and L. And the size of footing is length into breadth, that is 2.9 into 2.22, which is equals to 6.38 meters square. In step 3, we will be determining the thickness or depth of the footing. For this, net soil pressure is equals to only column load by actual area. Column load is 1000 and the actual area is 6.3. By dividing this, we will be getting as net soil pressure as 156.73 kN per meter square, where this is considered as applied load, where SBC is resisting load. Always net soil pressure should be less than safe bearing capacity. Then when we consider a footing, the critical section will be in the face of the column. So the depth depends on critical section. Then we have to calculate moment calculation. For that we have to take section x1 x1 and x2 x2. Section x1 x1 along the length and section x2 x2 along the width. From this we will be determining A and B, where we will be getting A as 1.15 meter and B as 0.875 meter. Then we should find moment along length, that is along M x1 x1. Since it is a cantilever beam, the load is 156.76 kilonewton per meter square and the perpendicular distance is 1.15 meter. First, the UDL should be converted into point load, since we will be multiplying the load into the distance, perpendicular distance, to convert this into a point load, that is 156.7 into 1.15, where this is converted to a point load, and we will be multiplying the half of the distance, that is 1.15 by 2. Then we will be getting moment about x1 as 103.61 kilonewton per meter. Then we should multiply factored load, factored moment. Then we will be getting as mu as 155.475 kilonewton per meter. Similarly, we should do it for along the width. Then we will be getting moment as moment about x2 will be getting as 89.79 kilonewton per meter square. Then we know that mu lim is equals to 0.138 FCK BD square, where mu lim is limiting moment, that is 155.42 into 10 to the power 6, 0.138 into 20 into 1000 into d square, where d is equals to 237.30. Based on shear conditions, we double the depth, that is d is equals to 237.30 into 2, where we will be getting as d as 480 mm. We will be providing clear cover of 60 mm. Then overall depth will be is equals to d plus d dash, where effective depth is 480 mm and clear cover is 60 mm. Therefore overall depth will be 540 mm. Therefore we got length as 2.9 meter, breadth as 2.2 meters and depth as 540 mm. In step 4, we will be calculating the reinforcement details, that is we will be calculating area of steel along longer span, where mu is equals to 0.87 Fy AST d 1 minus Fy AST divided by FCK into BD, where mu is 155.426 into 10 to the power 6, 0.87. Characteristic strength of steel is 415. Since we have to determine AST, it is unknown, and effective depth is 480 mm, and 1 minus 415 into AST divided by 20 into 1000 into 480. By solving this equation, we will be getting AST as 934.59 millimeter square. Then we should find spacing using 16 mm diabar, that is small AST by capital AST into 1000. Since we are using 16 mm diabar, spacing we will be getting around 215.13 mm. Therefore, we should provide 16 mm diabars at 210 mm center to center along longer span. Then we have to determine area of steel along shorter span. Similar procedure where mu value is 89.979 into 10 power 6, 0.87 into 415 into AST into 480 into 1 minus 415 into AST divided by 20 into 1000 into 480. By solving this equation, we will be getting AST as 531.4 millimeter square. Then we should provide spacing using 12 mm diabar. Then we will be getting the spacing as 212.829 mm. Therefore, we should provide 12 mm diabar at 210 mm center to center along shorter span. In step 5, we will be determining the shear force. Here we will be determining check for one shear. In one-way shear, the critical section will always be at a distance of d from face of the column. So we have to find the shear force at considering a section XX, that is V is equals to Q naught into A minus B, where Q naught is 156.73 into A minus D is 0.67. Therefore, we will be getting V as 105 kilonewton. If we multiply the factor, we will be getting as 157.51 kilonewton. Then we should calculate tau v. Then we'll be getting tau v as 0.38 Newton per mm square. Then we should find the percentage of steel, that is 100 AST by BD. Then percentage of steel will be getting as 0.19. By using the code book IS 456-2000, we'll be getting tau C as 0.312 Newton per mm square. Since tau v is greater than tau C, we have to change the depth, that is D is effective depth is 600 mm, effective cover is 60 mm, therefore overall depth is 660 mm. Since tau v is greater than tau C, we have revised the depth. Then we should check for two-way shear. In two-way shear, the critical section will be at a distance of d by 2. Then we have to find the perimeter, that is finding L0 and B0, and after that we will be getting B dash, that is perimeter, that is 4.5 meters. After getting the perimeter, we will be calculating the V value and we will be finding tau V value, that is 0.445 Newton per mm square. Then we will be finding the permissible shear stress, that is Ks into tau C. For that we will be calculating beta C and Ks values, and after getting both these values we will be finding tau C by the equation 0.2 times of FCK, that is 0.25 into root 20, that is tau C is equals to 1.11 Newton per mm square. Since tau C is greater than tau V, it is safe for two-way shear, and after this we will be sketching the reinforcement details, that is along the length we will be providing the longer bars of longer span, and along the shorter span we will be providing the bars of shorter length. Thank you.